Okay, we want to use shells to find the volume of each solid described below. We want to set up an integral, but we should not begin with an integral. We want to use our technique of slicing to build the integral from a single slice to a sum of all the slices, take a limit, and then finally an integral. And it says evaluate the integral using technology. We're not going to do that. We're just going to write down the integral. Okay, so my first solid is the solid generated when the region bounded by y equals x squared and y equals square root x, which I have sketched here already. So it's this region is rotated about the y-axis. Okay, so I'm going to draw the reflection on the other side of the axis of revolution. So I have a rectangle on the other side here. That is the reflection. And that's going to help me draw a picture of the cylindrical shell. So I'm going to connect that and like that. Okay. So you can see the cylindrical shell, and when you unravel that shell, you're going to get a shoebox. Unroll it, and you get a really skinny rectangular box. Teeny amount of thickness. The thickness will be the thickness of the rectangle you drew, which is delta x. Okay. The length of the shoebox is the circumference of the cylinder. So when you unroll it, the length used to be the circumference, and now it's the length. So to find the circumference, that's 2 pi r, where r is the distance from the center of the cylinder to the edge. So we'll call that r. And then the height of the shoebox is the height of the rectangle. It's the height of your cylinder. So this is h. All right, so r, my radius, is the distance from the center here, which is at x equals 0, to the random x value I chose as the location to draw my representative slice. So my radius in this case is x. So this is 2 pi x. And then the height of the rectangle is the length of this vertical slice, the distance from this point to this point. So it's y top minus y bottom. And y top is square root of 8x, and y bottom is x squared. Okay, so I have all the pieces for calculating the volume of this one slice. The volume of a slice is length times width times height, because it's a rectangular box. The length is 2 pi x. The width is the delta x. And the height is radical 8x minus x squared. And these are all at one specific x sub I location. This is just a single slice at a random location that I chose. We'll call x sub I. So I'm going to throw some i's on each of these x values here. And then I'm going to take the volume of all my slices, which is just a sum of n slices, where each slice has the volume 2 pi xi times radical 8 xi minus xi squared delta x. And then finally, I'm going to find the exact volume by taking the limit as the number of slices goes to infinity. So this is the limit as n goes to infinity of what I wrote up there. And that equals an integral. That's the definition of an integral. To translate, we drop the subscripts. So we have 2 pi x times radical 8x minus x squared. The delta x becomes a dx. And the last thing to figure out are the bounds of integration. So I'm going to go back up to my picture and figure out where am I drawing these representative slices, my representative rectangles that all get rotated about the axis. I am starting them about here at 0, and I'm going to draw n of them, as many as I can fit. Let n go to infinity. I have all these rectangles, and they are going to 2. So I'm starting at 0 and drawing all these representative rectangles, stacking them up from 0 to 2. So those are my bounds of integration, 0 to 2. Okay, for this next problem, I am rotating the region shown. It's bounded by e to the x, ln x, x equals 1, and x equals 3. Here's y equals ln x. This is y equals e to the x. And then x equals 1 and x equals 3 are the vertical lines. And we are revolving about the y-axis. We want to use the cylindrical shells method, which means I need to draw a representative slice within my region that is parallel to the axis of revolution. So I'm going to draw a representative slice right here. Little tiny rectangle within my region at a random location that I have chosen x sub I. I drew it at 2, but it's representing all of the possibilities of where I could have drawn that rectangle, so I'm calling the location x sub I. All right, so then I'm going to draw the reflection of this rectangle on the other side of the axis of revolution. So I get something that looks about like this. And then sketch the cylinder that results when I take my representative rectangle. It's going to come out of the board around the axis. It's going to land here on its reflection, and then it goes behind the board and continues to rotate. So I'm going to have a cylindrical shell that looks like this. Okay. When I unroll that cylindrical shell, it's going to look like a rectangular box. The thickness of that box is delta x because I drew my representative rectangle at location x and gave it a little bit of thickness, which is a distance along the x-axis. So it's delta x is my width of that rectangle, also the width of the unfolded cylinder. Okay, the length of this rectangle is the circumference of the cylindrical shell. When I unroll it, it used to be the circumference, and now it's the length of the rectangular box. So the circumference of a cylinder or of a circle is 2 pi r. So I need to know r here. So r is the distance from the center to the edge. So the center here is 0, x equals 0, and this is the random location I chose, x sub I. So this purple distance is just x sub I. That's the radius. So 2 pi x sub I. My vertical distance, my vertical height of the cylinder and of the unrolled cylinder, that's a rectangular box, is this distance, highlight it in a different color, from this point to this point. It's the height of my rectangle, which I can calculate by doing the larger y value minus the smaller y value. The larger y value is e to the x, and the smaller is ln x. So this is e to the x sub I minus ln of x sub I. That is the height. E to the x sub I minus ln x sub I. So the volume of my slice is length times width times height. Okay, length was 2 pi r, or 2 pi x sub I. The radius is at just x in this case. The width is delta x, and the height is e to the xi minus the ln of x sub I. So that's the volume of a single slice. Now I have to add up all of the slices. I'm going to have n of them, and each one has the same formula. I'm just using a different x to plug in here. So x1, x2, x3 up to xn. Each formula looks like this. And then I take the limit as the number of slices goes to infinity, and that gives me my volume exact. And the limit as n goes to infinity of a Riemann sum, that is the definition of an integral. And to convert from some limit of a Riemann sum to an integral, we drop the subscripts. So this becomes 2 pi x times e to the x minus ln x. Delta x becomes a dx. And I just have to figure out the bounds of integration. So I go back up to my picture and say, where am I drawing these slices? I picked one, x sub I, in the generating region. And so my slices in the generating region are going to start at 1. There's my first slice. And then I'm going to have a bunch of them. And I'm going to stack these slices up, each one getting rotated about the y-axis until I get to x equals 3. I'll have my last slice here. So my bounds of integration go from 1 to 3. And there is my integral for the solid. Okay, next one. We want to evaluate a volume formed by generating the solid pictured in the picture about the y-axis. So we have a formula for the curve, y equals 3x cubed minus 4x squared minus x plus 5 halves, and we are bounding it by x equals 0, x equals 4/3, and y equals 0. Okay, so I want to rotate this region about the y-axis. So I have to draw a representative slice somewhere in the region that is parallel to the axis of revolution. So maybe I'll pick this one right here. This is a representative slice. I happen to draw it right at 1/3, but it is representing the many slices I could draw anywhere in the region. So we're going to say it's at a random location x sub I. To get an idea of what this looks like when I rotate, I'm going to draw its reflection on the other side here. Here's my rectangle reflected on the other side of the axis of revolution. And I'm going to draw in my cylindrical shell. It's like that. Okay. So there's one representative cylindrical shell. When I unroll it, I'm going to get a rectangular box. And the thickness of that box is delta x. The length of the box is 2 pi r. The height of the box is the height of the rectangle. So let's see, r in this case is the center from the axis of revolution to the rectangle you drew. So in this case, it goes from x equals 0 to x equals whatever random location you chose, x sub I. So r is just x sub I for this problem. And then h is the height of the rectangle. So it's the height, the distance from this point to this point. So this point is on my curve, the cubic function, and this point is just 0. So my height is just the y value on 3x squared, 3x cubed minus 4x squared minus x plus 5 halves. So I have all the pieces I need to write a formula for the volume of this slice. The volume of that single slice, length times width times height. The length is the radius, 2 pi r. so 2 pi x sub I. The width is delta x. And then the height of the rectangle is 3 x sub I cubed minus 4 x sub I squared minus x sub I plus 5 halves. So that's the volume of my single slice. Now I'm going to add up all my slices. I have n of them. Volume of all the slices, I'm going to have I goes from 1 to n slices. Each slice has this formula for its volume. All we're going to be doing is subbing out different values of I. We're going to start with x1 and then x2 and then x3. And we might have like a million cylindrical shells at different x values. Then I take the limit as the number of slices goes to infinity. That gives me my exact volume of the region. And that is the definition of an integral. To translate, we drop the subscripts. So we have 2 pi x times 3x cubed minus 4x squared minus x plus 5 halves. And instead of delta x, I use dx. And then I figure out the bounds of integration by looking at the picture. Where am I drawing these representative rectangles? They're going to sweep through the generating region. So the first place I would draw one is right here at 0. And then I'm going to draw a whole bunch of them, stacking them up from 0 to 3. Sorry, I do not finish at 3. Go back up and look at that a little bit closer. The last rectangle I draw is at x equals 4/3. That is the end of the generating region. 0 to 4/3 are my bounds of integration. Okay, last one for these activities. I want to use the shell method to find the volume obtained by rotating this region about the line x equals -3. So I'm going to start by drawing the region. So I need to draw y equals x squared plus 2, y equals 6, and x equals 0. And this x equals 2 is a little unnecessary. Cross that off. X squared plus 2, y equals 6, and x equals 0. Okay, so y equals x squared plus 2. If you plug a 0 in there, you get 2. If you plug in a 1, you get 3. And if you plug in a 2, you get 6. So that's y equals x squared plus 2. Y equals 6 is this horizontal line. And x equals 0 is the y-axis. So this is my generating region. And I'm going to rotate it about the line x equals -3. So let's see, that is right here. That's my axis of revolution. So I need to pick a representative rectangular slice in the generating region parallel to the axis of revolution. So I'm going to pick maybe this slice right here, draw a representative rectangle, and I'm going to rotate that rectangle about the axis of revolution. Imagine it coming out of the board, rotating about the axis. We're going to see its reflection on the other side. And I'll have a little rectangle right here. And then it's going to continue to rotate back behind the board. So if I draw the shell that results, we've got something like this. There we go. So I have this cylindrical shell, a cylinder that's all hollowed out. It's very little thickness. When I unroll it, it's going to look like a very skinny box. Okay, the thickness of that box is just the thickness of the rectangle I drew, so delta x. The length of this box is the circumference of the cylinder. So I'm going to find the center of the cylinder and find the distance to the edge of the cylinder. So it's that horizontal distance. That's my radius. And so the distance between this x value and this x value is just the difference between the larger and the smaller x value. So r is x bigger minus x smaller. And in this case, this x value was a randomly chosen x sub I along the x-axis. And this x value is -3. So my radius is x sub I minus -3. And then the length of my rectangle is 2 pi r, the circumference of the cylinder. The height of the cylinder, h, is the height of the rectangle, this rectangle. So I'm looking for the vertical distance between this point and this point. So again, you're going to do the larger y value minus the smaller y value. So h is y big minus y small. This y value is bigger than this one, so this y value is 6. This y value is x squared plus 2. So my h is 6 minus x squared plus 2. So now I have enough to calculate the volume of a single slice. The volume of my single slice at a random x sub I location is length times width times height. The length is 2 pi r, and r is x plus 3. The width is delta x, and the height is sorry, that should have an I on it. 6 minus x sub I squared minus 2, or 4 minus x sub I squared. Now that I have the volume of a single slice, all I have to do is add up n of them, take the limit as n goes to infinity. So the volume of all the slices is the sum from I equals 1 to n of that, where each slice has that volume. And then the volume exact is the limit as the number of slices goes to infinity. And that is the limit of a Riemann sum, which is the definition of an integral. So this becomes 2 pi times x plus 3 times 4 minus x squared dx. And then I need to find my bounds of integration by looking at my picture. Where am I drawing these representative rectangles? I'm sweeping them through the generating region. So my first rectangle would be drawn right here at x equals 0. And then I'm stacking up these rectangles, each one sweeping out a cylindrical shell. And I finish at x equals 2. So I'm stacking up these rectangles from 0 to 2. Those are my bounds of integration. And so for this last question, you were asked to evaluate this integral by hand. So since I'm going to do that, I'm going to pull the 2 pi out of the integral because it's just a constant. And then I'm going to multiply these two parentheses together. So I have 4x minus x cubed plus 12 minus 3x squared dx. So I can now just integrate term by term and use the fundamental theorem of calculus. So I'll write this out over here. So 2 pi times, I'm going to integrate term by term. So the antiderivative of 4x would be 2x squared. Antiderivative of x cubed is x to the 4th over 4. 12x minus x cubed evaluated from 0 to 2. Okay, so if I plug in a 2, I get 4 times 2 is 8. 2 to the 4th is 16 over 4 is 4. 12 times 2 is 24 minus 2. And then when I plug in a 0, I get 0. So this is 2 pi times negative 12 plus 24 is 8 minus 4 is 4. 4 plus 24 is 28. Minus 2 is 26. Okay, I just realized I made a little mistake when I was plugging in the 2. So I plugged the 2 into each of x value. So I'm plugging this 2 into each of these terms. So 2x squared is 8, x to the 4th over 4, that's 2 to the 4th is 16 over 4 is 4. 12 times 2 is 24, but then I forgot to cube this last one. So 2 cubed is not 2, it's 8. So this should be minus 8. All right, so that comes out to now 20. So 2 pi times 20 is 40